Alright. Hello, good evening everyone again. We are back to DanDoesData, continuing to look at Keras, and tonight we'll be looking at recurrent neural networks, a new topic for the show. Hopefully it'll be pretty interesting. It's something that's pretty new to me, so bear with me as I learn while I go here. Should be alright though. You might notice I have a slightly new console. I got kind of tired of Xterm and it was kind of small, so I'm using an actual console to do this now. We'll see how I like it. It might break certain things. Other things might be totally okay. If you hate it, let me know, and I'll file that in the trash bin. But probably I'm going to be sticking with this for a little bit. That's okay. Okay. So actually, excuse me. Recurrent nets, I didn't find a good tutorial in Keras on recurrent nets, which I was a little bummed. And that's really what I want to just walk our way through. Maybe there's one on Theano. Recurrent nets. Deep learning, there we go. So a recurrent neural network is something you use. Is something you use when you sort of have data in time. So if you look at a bunch of population over many years, say, and you take a sample once per year, you can sort of use a recurrent net to keep information from last year and use that in this year's estimate. Anything with that kind of dimensionality to it is something that makes sense. So like video is another place where this might make sense, or as we're probably going to see today, language. If you're like modeling words in a sentence or something, you're going to get that kind of a feature where there's several words back is where I was. You can sort of think of a convolution in the same way if you really want to, but the recurrent neural nets are going to be very different. Basically, we're going to be using features from a previous data point. So our data points have to be nice and ordered. For example, frames of a video. We'll be using features from the previous data point and the current data point. And this does weird things to the calculus, but that's okay. This has all sort of been worked out. So where can we get the old small benchmark for this is ATIS, Airline Travel Information System. Well, what is this? Recurrent neural networks with word embeddings. Learn word embeddings using recurrent neural network architectures with context windows. I assume that's how far back you're willing to learn. Papers. Contact, task, slot filling, spoken language understanding consists of assigning a label to each word given a sentence. It's a classification task. Okay. An old and small benchmark for this, collected by DARPA. Wow. Here's a sentence or utterance sample using inside-outside beginning representation. I don't know what that means. Boston to New York. York. Oh, show flights from Boston to New York. BDEPT, BRBR, date. Contains 5,000/893 sentences for a total of yada yada this many words in the train/test set. Number of classes. As Microsoft Research people, I did not know deeplearning.net was run by Microsoft Research. That's interesting. I learn something new every day. What do you know? We deal with unseen words in test set by making stuff happen. 1 second here. Okay. Making stuff happen. Recurrent neural net model. A token corresponds to a word. Each token in the vocabulary is associated to an index. Right, so you just number all the possible words that you have. Each sentence is an array of indices. Right. So you've got at most 2 to the 32 different unique words. In fact, there are maybe 56,000 words. Probably less than that. Then each set, train, valid, test, is a list of arrays of indices. Right, so you're trying to predict what the sentence is. Each word is, so 383 represents please, 189 represents find, 13 represents A. I'm betting these are sorted by frequency, so the most common words have smaller indices. For example, 2 is probably a 7. Unknown is probably an 8. Not surprising. Okay. Python dictionary is defined for mapping the space of indices to the space of words. Okay, I guess you can do it that way. I would just use a list, but that's okay. The same thing for labels corresponding to a particular sentence. Labels. B from lock dot city name, B from lock dot state name, B to lock dot city name. I'm not sure what what are the labels here? Output, labels. Maybe I should learn about inside, outside, beginning. Common tagging format for tokens in computational linguistics, which if you're familiar with XKCD, you can choose any number of wildly contradictory models of computational linguistics and you'll be fine. As a random aside, B prefix before tag indicates that tag is the beginning of a chunk. The I before tag indicates that the chunk is inside. The B tag is used only when the tag is followed by a tag of the same type without O tokens between them. An O tag indicates that the token belongs to no chunk. So I've got the B prefix before a tag indicates the tag is the beginning. The I says it's in the middle. Let's take a look at this again. Show flights from Boston. So this is the beginning. This is the beginning of a tag. Then there's O, so it's nothing. It's not a token. To new is the beginning of a tag. York is the inside of a tag, so it has an I. And today is the beginning of a tag. So I'm gonna guess, without looking at this further, the goal is to predict: is this word an other, a beginning of a tag, a inside of a tag? 3 classes maybe. And maybe I want to know if it's the beginning of departure, beginning arrival, beginning date maybe. Okay. Context window. Given a sentence, i.e. an array of indices, indexes, whatever, a window size, we need to convert each word in the sentence to a context window surrounding this particular word in detail. Okay, int corresponding to the size of a window, so you're going to look at a few words at a time. L, array containing the word indices. L being the giant array of all possible word indices, I assume. If L equals list L. Yeah, so you copy your L. Index -1 corresponding to the padding index we insert at the beginning / end of a sentence. L padded. What is when? Assert that when you have an odd number of, that your window size is odd? Alright. And that it's at least 1. Return a list of indices corresponding to context windows surrounding each word in a sentence. Here is a sample. 0, 1, 2, 3, 4. Your context window starts at -1 and slides through all. Oh, okay. You're just taking sliding windows of whatever the heck your sentence is. I feel like they made this seem much more complicated than they needed to. And if you don't actually have a word there, you put a -1. So 0 is really, of course, the first word of whatever the sentence is. You put -1s here and -1s at the very end in the last possible window. And is the 3 because they need it to be 3 long? Once you have, and you stop, when do you stop here? Why didn't I go one further? For example, just at 4, -1, -1. That's what I want to know. Because we wanted 5 things? This is interesting. Or because we need to see every possible... No. Like, why is this 5 things? Is it always 5 things? Return a list of indices corresponding to context windows surrounding each word in the sentence. Out equals for I in range length L. So you're getting a context window for each. I see. Read down the middle here. You want a window of this length centered on each element of your sentence. Now it all makes sense. That's why there's 5, because there's 5 inputs. Again, this is a terrible explanation for what they're really doing here. Just take a window, stick the index in the middle. What are the things to the right and to the left of it? Is your window 3 big or 7 big? And that explains why it has to be odd, for example. because you want yours in the center and the same number on the left and on the right. Okay. Word embeddings. So that's, okay, that actually makes sense. So we're going to end up generating a whole bunch of data from this. Note that this 5 long thing here turns into a 15 long thing here, right, 3 by 5, and a 35 long thing here, 7 by 5. So your data size is going to grow quite a bit, so you have to be careful. But where do we get those embeddings, my friend? Elman Recurrent Network. That's cool. Interesting. Never heard of that. What if... There's a lot here. Okay. Data sets. Can we actually get our hands on the data set? Code? Maybe this will explain the code, the data? Load.py. What have we got here? os.getenv? No. Download. Oh, okay. This will download the data for me. That might be a little complicated. What have we got in the... So TensorFlow, which Keras can use, but we're choosing not to use that way because I want to use my GPU, also has a recurrent neural net tutorial doing some language modeling. I don't know what exactly kind of language modeling, however. It's in directory of PTB dataset of Thomas Mikolov's page. They do an LSTM, truncated backpropagation. They define the loss function, then they just say, hey, run our code. But they don't walk you through what the code does. That's a little bit of a bummer. Alright, we're going to close that. Here's what I'm going to try. Here's what we're going to try here. We, I think, are going to try to do this. With this word embeddings baloney. See how complicated that really gets. Raw input encoding, context window. This takes me right back here, doesn't it? Is this different? This, I feel like this is just gonna... Okay, yes, this is the same thing I was at. Just didn't look like it. And this talks about the fancy Elman recurrent network, which we will dutifully ignore. Evaluation, updates, stopping criterion, hyperparameter selection, yada yada, running the code, do some timing. Word embeddings, nearest neighbors. Check the k nearest neighbors of the learned words. L2 and cosine. Right, so words that are likely to be next to each other. Atlanta, Phoenix, Denver, Tacoma, yeah, cities. All this other stuff. Okay, so our goal is to classify, I think, what kind of token it is. That is my understanding. Oh, the number of classes is 128, including the O label. Okay, there's a lot of different possible classes. But hopefully they've given me plenty of data in terms of that. I guess all classes are hopefully represented a reasonable number of times. The number of classes, alright. Right, so we've sort of got one feature, the input word, but the recurrent part is we'll be looking back at previous words to help us understand what the kind of token we're dealing with. And we're not literally going to be looking back at those words. We're probably going to be looking at some neural net derived feature of those words until we get to that point. I really wish they just put a download link on this page though. That would have been helpful. Alright. I want this, and I want the raw. No, not the blame, the raw. And I can save page as. Not load.py, that's a silly name. Yeah, load.py is fine. Okay. Let's move that from my downloads, load.py. Let's put that here. Let's have edit then, shall we? Import load. IPython. Here we go. IPython, yeah. Oh god, everything is Python. What is wrong with people? Why do people love Python 2? I don't understand. And if you do, why do you want to use print in this way? Like, to me, that's just a weird way to use print. Oh my goodness. I don't get it. I used to use Python 2 for a long time as well, and I still never use print that way. I almost always put the parens into place. You save a little bit of time for a big headache later. Alright, let's see if we can import load now. Okay, we can. Alright. Now, let's learn how this load actually works. How are we going to get our hands on the data? Download Dropbox, load Dropbox, yada 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 yada. Import PDB. Let's close that down. Oh, this is like the proper paper. Oh, I see. Interesting. Is this even the right data set then? That's the real question. Airline travel information system. So how did I end up getting to this? How did I get to this page then? Does anyone remember that? Precision, recall, F1 score, that's all typical stuff. Directly running experiments is also possible. That's how I got here. Okay. So is this some wacky ATIS data? Code. ATIS data. Download ATIS dataset here. Perfect. That's actually what I want. Perfect. Let me download it. Let's just download. How much is it? 3 megabytes? Boom, get it. Get all of it. Forget this load baloney. That's silly. I'm not doing that. Inevitably, I just want to be able to load my dataset in a simple way. Alright, let's grab a bunch of Keras stuff that we're going to like. There we go. Sequential, dense, dropout activation. We're going to need recurrent. Keras.layers.recurrent.recurrent. So that's from keras.layers.recurrent import recurrent. Make sure I spell it. I sometimes think it has an A in it. That's not true. It does not have an A. I don't think we're going to need convolution in this stuff. Let's get rid of that. We probably do still need dense in this other stuff. We might need this one hot business. Let's do all this. Let's turn our IPython back on first. I kind of dig this like blue and green. It's like reminds me of like a small pond or something. There's like frogs and lily pad. It's very soothing. Very soothing. I'm about to get burned. Yeah. That's what I get. Because C pickle. Oh, you Python 2 people. Oh my gosh. Like at least they could use 6 if they're gonna be like that. Okay. Move, downloads, ATIS. What is it called? Freaking, come on. ATIS. Star.pickle. Did I not actually download this? I didn't actually download this apparently. That's awful strange to me. Pretty sure I did. I clicked the download button. I said open with gedit apparently. No, I didn't. Hey, what do you know? ATIS right there. Let's move it to the current directory. Okay, superb. Close that off. Do this again. Bytes like object is required, not string. Right. Python 2. ASCII codec cannot decode byte and mother border. I'm going to spend most of my life fighting Python 2 versus Python 3 errors, I swear. That is probably 90% of my existence. I learned how to solve this before. Is it with the load codec or just with open? Unicode decoder, I think is with load. Pickle.load. Optional keyword arguments are fixed imports, encoding, and errors used to control compatibility for pickle stream generated by Python 2. Fixed imports is true. Pickle will try to map the old Python 2 names to new names used in Python 3. The encoding errors tell Pickle how to decode 8-bit. Default to ASCII and straight respectively. The encoding can be bytes to read these 8-bit string instances as byte objects. Coding equals bytes. Let's try that. There we go. Train. Okay, test. That looks like stuff. Okay, now we're getting somewhere. Now we're cooking. I feel much better once I have some like actual data that I can look at. It's just it's considerably more soothing. In fact, let me plot .p color mesh. Let's just look at some. I don't know, the first 5. What's list map lang of train? Is that what I want? Nuppy.min. That's my shortest, really? Wow. Max. Are these all the exact same length? Or am I not using this right? Let's find out. There's only 3? What? Train 0. Train 1. Train 2. What are these? These are some kind of the... Oh, man. There we go. Go back here. Data. Dix is a Python dictionary that contains the mapping from the labels, the name entities, and the words used in train and tests. Refer to this tutorial for more details. Okay. Yeah, thanks. That's real helpful. Real helpful. So why is there train 0, 0, train 1, 0, train 2, 0? So this is some strange encoding, and it looks like this encoding is the same as this encoding, just different numbers. 0 goes to 126. I got some really weird. It's not interpreting my my console width correctly. One downside of the console over Xterm, I guess. Oh well, that happens. Yeah, that's, I don't know why that is, what to make of that. Why would I use this one over this one? These are my labels, I think. These are like what word it is. These are other labels that you can use. Dix.keys. Tables to index, labels to index, words to index. Tables to index. Labels to index. Words to index. Do I have words? Is that something I get? What are my values? Hey, what do you know? Okay, so one of them is just, I get to see the actual words, such as digit, 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 digit. Digit, 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 digit. There we go. Midwest, etc., etc. And these are all byte strings, because we're in Python 3. We are living in the modern era. All right. So this is kind of a strange. The key is like what word it is. And that tells you what the index number is. But they give me words to index. That's really strange. So 126, 126, 126, 126. But they don't give me a dictionary of... Hang on. I don't get an index to words dictionary. That's really what I need, right? Otherwise, I got to scan through this whole damn dictionary looking for something with the correct value and what word does that map to. Because I'm willing to bet if I take a look at the length of the set of dicts. Let's see. Dicts. Let's think about this right. Dict keys. If we say dicts of words to index. Words to index. That's, of course, it's a byte string. This gives me a dictionary keyed on the word to give me the actual index. Right. But I have the index, and I'd rather get my hands on the word. So you have to invert the dictionary to get something useful out of that. In fact, why don't we do that right now? Why don't we say index to words? Something maybe a little more useful here. Is dicts of words to index. Okay. We should be able to do this the easy way of v comma k for k comma v in this dot items. Items. And we'll learn if it's really a dictionary or not. What did I do here? Sequence, there we go. There we go. Now, given an index, you can actually look up what the heck word you're dealing with. I don't know why it wasn't just that way to begin with. Let's do likewise for the labels. And we'll learn why these silly people do this the way they do. Labels. Is that an actual thing? Index to labels. Okay. And now we can see what the various labels are. There's 126 of them, it looks like. Probably 127. Yeah, 127. So 0 goes to B, aircraft code, B, the beginning tokens, versus I, sort of inside tokens, continuing tokens. What a headache. So our goal is to take the words that we have, in, for example, train 0, 0, and map those to the labels that we have in something like that. Are those my labels? No. Those are, no. 0, 0, 1, 0. There we go. Those are the labels. And those are, no, those are the labels. Dict.keys again. Look at this. Dicts.keys. Tables to index, labels to index, words to index. What is tables in this context? You know, that doesn't really matter. We converted sequences of numbers with a string digit, IAG 1984, to digit. It's already been split. We're looking at precision, recall, and F1 score. How well do you... here, let me just show you. Right. Precision, fraction of achieved instances that are relevant. Recall, precision that are retrieved. What a strange way to look at that. So how many things did we get correct over all things did we want to find? How many things did we get correct out of all things that we, or not how many things did we get correct? How many things did we find out of all things that there were to find? How many things did we find out of all things that we said we found? Two different measures, sort of. Do you worry more about false positives or false negatives? And F1 score can combine them into one number. That sort of gives you an idea of how well your model's doing in both. Recurrent neural network model. So the sentence, index to word X. See, yeah, I wrote an index to word thing, and your code didn't have that. At least the data set that I had didn't have that. It was whatever. Whatever. So we've already written our index to label and index to word. So that's fantastic. So actually, let's do the stupid thing. Train 0, 0. That is, of course, our first sentence there. And we're going to map, let's do a list map of index to words. What do they do here? They put a lambda? Yeah, not surprising. Lambda x, index to words of w. And we're passing in that as our output. So this should give us X, not W. There we go. I want to fly from Boston at blank, 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 and arrive in Denver at blank, 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 blank in the morning. Not sure what's going on here, but that's okay. So context window. I'm going to be a bad person. I'm going to copy this. But you can. There's a ton of ways to do this, though, that are all about the same. Let's set pace so I don't go crazy. There we go. Perfect. Let me delete all this doc string. We don't need that, right? No, I'm just trying to save a little space here. So yeah, just make the window. Oh, why is my... Oh, it's terrible. Terrible. I don't know why. Set soft tab. Set tab width equal 4. Never mind. My Vim is going a little weird. That's okay though. So this will return a window around each character of our sentence. So if you have a one long sentence, you get a window that's going to be -1, -1. Your character, -1, -1. If you've got two, you'll get two windows back out. In fact, let's just run context win of whatever our sentence was. Train 0, 0. We like to use that one. And how long do we want our window to be? Let's say 4. Nope, it has to be odd. 5. And there you can see. You look at the first character, and you pad to the left, you put the character in the center, and then you look at things to the right. And so these are probably going to be the features that we're dealing with. And I'm betting we're trying to predict in the center. Is this the beginning of something? Is it the inside of something? Is it something we're not actually interested in? Things like that. Word embeddings. What is this? Once we have a sentence converted to context windows, yada yada. Oh, so we should convert all of our... Or we can do that live, whatever. Sentence converted to context windows, a matrix of indices, yada yada. Associate these indices to the embeddings, real valued vector associated with these words. Embedding. What is the embedding? What is this? Theano.shared 0.2 times numpy random. What is this? Size of our vocabulary, dimension of the embedding space. Oh, is this the labels that we're getting? Theano.shared, so we're taking some random value. We're initializing this to a random value anyway. It's some float of the size of our vocabulary +1 apparently. Interesting. Of 1,000 word vocabulary. No, excuse me. Yes, with 50 labels, I guess. Context window size being a 5 long window. I don't know why we have to associate these indices to the embeddings, real valued vector associated with each word. The X symbolic variable corresponds to a matrix of shape, number of words in a sentence, dimension of the embedding, space X. Let's compile it. What? This is coming out of left field for me. Sequence of length 5, which corresponds to the length of the sentence. Did they just take whatever these values are and convert them to floats? Is that what happened? So yeah, this just initializes some space. And I think all they're doing here, really, DE times CS, that's just the right size. As many columns as words in the context window and as many lines as words in the sentence. Self.emb. Take a self.emb. That's, if in this little miniature code snippet, that is not defined. This is missing some key phrase here. Self.emb. Interesting. Okay. T.imatrix. I mean, that's a Theano thing, sure. Import backend is okay. Let's make sure we get our backend so we can do this. Backend is K. We have sequence classification, right? Word level embedding. Oh hey, maximum caption of maximum length 16 words. This is almost the right thing, right? Embedding. Max features 256, input length. So what does embedding actually do? From Keras.layers import embedding. Let's take a look at layers. This must be a core layer? Maybe, maybe not. We'll find out here. No, not one of those. Embedding. Not actually there. Just, is there an embedding layer? Embedding layers, what do you know? True positive integers into dense vectors of fixed size. So we divide? Wait. Here they're turning a vector into a dense matrix. Interesting. So this is another representation of this, apparently. Input dimension, output dimension, uniform, yada 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 yada. Alright, this might be showing my lack of understanding of the recurrent problem. I think we're just expanding the feature space a little bit. Dimension of the dense embedding. So we want more features. References, something talking about dropouts. Let me ask the internet. Dense embedding. Let's see if we can learn about this in 30 seconds. That's always a risk. Oh boy, in topology, it's not really what we want. Neural net. Primary neural network models for natural language modeling. What is an embedding layer in a neural network? Stack Overflow. Someone who has a similar problem to us right now. Like Keras or lasagna. Pasting documentation. There's not much to paste from the documentation, hence my question, yeah. Recent Word2Vec innovation. I thought the Word2Vec. So Word2Vec is a library neural net model that takes words that you have and maps them to like a 300-dimensional space or something like that. It's like the inside features of some neural network. And so in that space, like words are interesting. And so does this just do that? Hope is that by using continuous representation. Oh, continuous. Yeah, okay. Okay, more concretely, let's break down lasagna code snippet, yada yada yada. Yeah, lasagna is another neural net library. It's probably a little similar to Keras. I'll probably look at that at some point. It's our word embedding matrix. It's 3-row by 5-column. Okay, and how do you determine how to do the transformation? Our vocabulary has 3 words, and we will embed our words into a 5-dimensional vector space. Really? Yes, each word gets a 5-dimensional representation. Okay. And like, is that something we're gonna compute, I guess? We're gonna compute what that is? I think that is what I'm understanding. What X-test means. We wish to embed our 2 grams using the word embedding below. That 3 does indeed represent the vocabulary size. Try inputting in matrix X real tests. Yes, there's only 3 different things here because they have 3 words in their magical embedding. Okay, so I guess this is a typical way to attack the problem, which is interesting. I wasn't aware of this. Represent word 1 equals 100, another 1010, another 1001. That's hot, sparse encoding. It's the one hot business. We give you W as a matrix embedding these words via matrix multiplication. Therefore, our first word, W0, equals this. W1 equals this. W times, what is W? So how do you get your hands on W? Is W what gets trained? I'm really thinking that W is trained. Apply the word embedding matrix W via right multiplication to this sparse matrix. Applying our embedding matrix W to this sparse matrix. Oh, hang on. Let's make sure we're clear. The 2 gram W0, W1 is equivalent to whatever. So you just put down your lines. Is that how they really do it? You just take whatever this thing is and you line them up. So this one is 0 through 4 for the first word, 5 through 9 for the next word, 10 through 14 for the last word. I mean, that'd be kind of goofy. That might be the case. So we're going to generate a new set of features for each word and use that to, and we're essentially going to climb on that then, which is sort of what neural networks are all about anyway. So embedding layer, that's what we need first. Right. Keras.layers.embeddings.embedding. Let's go up there. So we're definitely not going to finish this tonight, and that's okay. We don't have to. Yeah, from Keras.layers.embeddings, import embedding. See how that works. There we go. Beautiful. So let's just slap down. Let me grab some scaffolding here. We do have a sequential model. But we're going to say model.add embedding first. And what kind of embedding are we going to do according to this? Oh boy, oh boy, oh boy. We've got 1,000 long space, do we? Is that true? Is that true? Index to words. How long is this? Is it 1,000 long? 572. So that's the size of my vocabulary, 572. In a day, yeah, this bit, this is some sorcery here. Not sure how they're coming up with that business. Input the current time, the previous hidden state, and then it iterates. Previous section, we process the input to fit this sequential temporal nature. Parameters, the hyperparameters are, embedding. Max features, 256. Input length equals max length. The frick is max length in this situation? Oh, the maximum length of how many of my sentence, perhaps? I bet that's what it is. Max features, which I suppose is how many, let me just say, it's how many different words I've got. That's what I'm going to suppose it is anyway. IDX 2 words. Plus 1, because I've got kind of like the padding, the null. How many output things do I want? Right. Generally you want more? Less? I thought you wanted a shape there. Can embedding take a shape? Input dimension, output dimension. There we go. Yeah. So 16 by 16, 32 by 32. 32 by 32 is 1024. Yeah, let's try that. Oh, this is gonna be real annoying. Hang on. Elf Lord. What? Oh man. Really? Hang on. Yeah, screw it. I'm annoyed that these numbers are highlighted. That's a little silly for me. Does it do with the tuples? It does. But just normal numbers, it certainly doesn't. I'm an idiot. I was searching on 32. Never mind, I'm an idiot. Alright, so we're going to transform our input into this 32 by 32 business. And what are we working with? Input length equals max length. So what is the maximum length of one of our sentences? So lmat list map of what do I want to do? Length, what am I calling on? Train. What is train? Train is a list. What is train 0? 0, 0 versus 0, Okay. No, I want 0. Just all those guys. Yeah. List map length of train 0. There we go. Let's ask for the maximum of that. Let me just get just call this longest. Numpy dot max list map length train 0. All right, we got it. Yeah, much better. Okay. Input length equals max length. Sure. But the input length isn't going to equal a max length. My input length is actually going to be whatever my window size is. I think, anyway. Window size. Let's call it W. Let's say 5. W. I think that makes sense. I'm not 100% sure, to be honest. And then they just do, here they got like, oh, do LSTM. Yeah, well, we're not going to be doing just LSTM. We want to use recurrent neural nets. Recurrent. There we go. So model.add recurrent. And how do we use recurrent? Do they give an example? Simple RNN. Fully connected RNN where the output is to be fed back to input. That is really tempting. GRU. Gated recurrent unit, no. LSTM, also interesting. LSTM is this cool little circuit that helps you where certain things get remembered and certain things get forgotten based on whatever those features actually are. So it's kind of neat. Parameters of this network. All right, hang on. Maybe we can figure it out just by reading the Theano code here. Element recurrent net model. They've got, looks like 2 layers. It's WX, WH, unless this is just like X and Y kind of stuff. And then some bias units. And H0 is probably the hidden type layer. These are parameters. Recurrence. Here we go. Here they're defining the recurrent net operator. So they're taking the input X of t's, whatever those are, and they're just doing a standard matrix multiply plus this other stuff. I assume that's the previous layer, or not previous layer, excuse me, previous time step, h time minus 1, tm1, of course, times self.wh. Oh, so that's the history, the historical. And you compute h of t, and then s of t takes h of t and hits it. This is just a densely connected. Oh, this just goes into your logistic right away. Okay. That's interesting. So this, something like this maybe? Embedding, recurrent, and then... Alright, how do I use this recurrent? Really, how do I really use the recurrent? Don't be yanking my chain here. I'm I'm really tempted to use Simple RNN, where the output is fed back into input. Oh, so you don't even dimension of the internal. Note I'm using dropout with TensorFlow. Yeah, don't worry about it. We're not using TensorFlow right now. All right, we got 10 minutes left. Let's see if we can get a model that runs, even if it doesn't work. Do not use a model. It's not a functional error. Whoops. Simple RNN. That's the one we want. Okay, let's go back. Where do we get that? Here we go. Simple RNN. Perfect. That's what we want. We don't want to be using the abstract classes. Alright, does this have a little more explanations? Output dimension, inner init. Is there an example of the LSTM sequence here? Just hoping it's the output dimension here. 128. So how many things do I want out to come out of it, I think? Which I believe is here. And I got so many things open right now. Yeah, so how many nodes are sort of coming out of this? I don't know. 32 is a popular number. Let's do that just to see what happens. This is no longer 10. Our final thing we're classifying into in one of length of index to labels, right? So not W, N labels, length of index to labels. Make sure that goes. Okay. And labels. Perfect. What's the minimum I can get away with here? Activation. All this other stuff looks like it's determined. Let's see if I can just get away with that. Yeah? So we're embedding. We're doing a simple RNN. We are dangerously misunderstanding what's going on. And that seems to be the skinny of it here. Let's see if this model even goes. I'm curious if it will even allow me to load it. Even allow me to load it, provided I pass the correct number of parentheses. Nope. Oh. Int object is not callable. Interesting. Oh, I probably need to state that that is. Not the output dimension. The input length. Input length. Otherwise, it's going to get inferred. It's required if you're going to connect, flatten, then dense layers upstream. Right. Input length equals there. There we go. An integer is required. Isn't W an integer? All those things are integers, buddy. All those things are integers. Embedding, what is it not like here? mtrand at random uniform. Interesting. Interesting, interesting, interesting. What is, there was an example with embedding, right? Could have sworn there was an example with embedding. In examples. Yeah. Max features, 256. Oh, it doesn't want a list? I really thought it wanted a list. Alright, well, 1024 then. I thought that was just output dimension. That is, yeah, output dim. Int greater than or equal to 0. Dimension of the dense embedding. Alright. No, right. I'm an idiot. It will compute the input times the output. Or excuse me, the input times the output for me. Doop-de-doop. Alright, things are happening. Things are happening. Things are happening. Let's compile it because we can do that. Now, actually setting up our data correctly is going to be the catch here. Because we need to run this context business on all of our training data, and we got to convert our labels to one hot format. Thankfully, we can do that with numpy utils, because we did that over here. Numpy utils.toCategorical. There we go. Let me load that in over here somewhere. Sure. Why test? Where's my actual data? Test. Yeah. I like test hot. And that'll just go with test and, hang on, how many classes are there? That's determined down here. And labels. All right, we got 5 minutes. Does that work? Oh, we're still compiling. Well, we do what we can, you know? We might have to revisit this next week. All right, let's see if I can use up all the memory on machine when I do this context win business. Let's let us find out. Oh, that almost certainly didn't work, actually. Yeah, I highly doubt test did the right thing. Or train did the right thing. Yeah, that's not going to work. Because train, it's not just train, it's train of 1 and 1. There we go. Of all my various. Oh, and I got to do that. That's a sequence of labels in a word. Hang on, hang on. So I need to map. It's like I gotta, yeah. I gotta flatten this out. This is gonna take a little time to do. Today, and of course in their example, they don't actually go through any data. They just say, hey, run these commands, which is great. Let me spend 2 seconds searching for Keras RNN example. Example, predicting sequence of vectors regression in Keras. Sure, add character-based RNN example. Someone's got a pull request for this. I mean, that's interesting. Oh well. Alright, so I don't think we're gonna get to actually run the model tonight. Although, yeah, I don't think so. I gotta fiddle with this training and testing data set, getting those to the right things. Then we gotta run context win on all of our train win, for example. It's gonna be like context win of whatever our current T is and W for T in train 0. Yeah. Those are going to be all of our contexts. And then we can substitute train test. Do that. And I think we can do the same business here. Alright, hang on. Maybe this isn't going to be that bad. For T in train 1. There we go. For T in train 1. And of course, this shouldn't be that. See how bad is this? Actually, let me import from TQDM, import TQDM. And then we'll put this over here. TQDM is a nice progress bar that belongs on everything ever. Oh, never mind. That was very quick. Okay. Index 29 is out of bounds. Interesting. Same problem. Interesting. And labels plus 1, and labels plus 1. Right. Right. And then this needs to be freaking compiled. Just to be in labels. And labels, there we go. No, that's not right. It's still gonna be, yeah. How many words am I working with? No, index 2 words. Yeah, sure. Sure. How many words are there? And there's a word for no word? Yeah, there's a word for there's no word because it's padding. And there's a label for padding. Okay. Still doesn't like that, man. And labels for axis with size 128. Listen, buddy. Let's add one more. Maybe the zeroness is not right on these. Oh, come on. Fine, we'll jack these up even higher. Index 139. Alright, it's doing stupid stuff. It's doing real stupid stuff. That's clearly not the actual number of labels. And labels, 128. Oh, here's the question. Length of index to labels, 127. Oh, but the actual labels they use, I bet, are bigger than that for whatever stupid reason. Dot keys. No? Oh. Train 1, 0? That's weird. Train 1, 1, 2. What the heck? Alright. I don't know why that is. No, I don't want to know how long something is. Hang on. I just want to know what's the maximum thing in any one of these. What's the biggest value in this? Yeah, figures. Of map. Hang on. numpy.max of this. Cute. Right. Inevitably, I actually want the list. 140. So this is a mystery to me. When it says there are 128 labels, and then it gives me 140 labels. So who knows? I think on that note, we're going to have to let it go. Why are there 140 labels if there's not actually? Because I'm using the wrong value. That's what it is. This should be trained 2 in all contexts. 2 is the actual labels. Train 1 is something else. Alright, we did this business, and labels is whatever it is. We compiled. Alright, let me just try it real quick. Train W. Yeah. Train hot. I don't care about the validation data right now. Batch size equals 16, say, whatever. I'm just going to pass in the first set because train W0 should be a bunch. Yeah. Does this even run? All input arrays and target array must have the same number of samples. Train hot 0. That didn't work. Right? Versus length of train W0. No, that did work. Screw you, you're a hippie, man. Oh, it didn't like my input length, maybe. Or my embedding baloney. Maybe it didn't like that. Alright, we will continue fighting with Keras, recurrent neural networks next week. But for now, we're just satisfied with learning a whole lot about it and doing some embeddings and getting our hands on the data. At least we were able to get a model to compile. So that's a start. We will be back next week with more recurrent networks and Keras. Till then, have a good night.